Thank you. First of all, I would like to thank the organisers for asking me to speak here. This is the first time I've spoken in Utrecht. Okay, so this is kind of a survey of some things I've been thinking about for quite a while, and I'll try to explain my perspective at the moment. First of all, I want to review the standard picture, which probably people here know quite well to start off with. So basically, if I fix a compact or a Riemann surface, perhaps with boundary, and choose a connected complex reductive group G, it's possible to attach to that a Poisson space. The homomorphisms from the fundamental group of the surface into our group defines modulo G up to conjugation. This has a natural Poisson structure that has been looked at by many different people, and people are interested in it for different reasons. The first perspective was probably the infinite dimensional perspective of a Tier and Bott, and after that there was a more algebraic perspective of Goldman, and then lots of other people also looked at it completely algebraically, and there were sort of various different algebraic constructions of the Poisson structure on this space. So a Tier and Bott looked at the case of compact groups, and this case was particularly interesting because then the spaces are isomorphic to moduli spaces of stable G bundles. They have Kähler structures. Here I'm more interested in the case of complex groups, so complexifications of compact groups, and these have sort of especially rich geometric structures also. In particular, Hitchin proved that the generic symplectic leaves are hyper-Kähler manifolds, which are often complete. So it's in spaces which have interesting metrics, not just the Poisson structures. Today I want to focus more on the Poisson and symplectic aspects, but perhaps the reason why the spaces are interesting is because they have these metrics as well. Okay, so the perspective on these which I prefer is the Lie group valued moment map perspective of Alexeyev, Malkin and Mine-Renken, and the basic statement can be phrased in this way. So suppose our surface has m boundary components, 1 up to m, so each boundary is isomorphic to a circle, and choose a single base point in each boundary component. Then look at the fundamental groupoid of this surface, so homotopy classes of paths such that the ends are on one of the base points. Okay, and then the basic statement is that the space of representations of this groupoid into the group G is a smooth affine variety which is naturally a quasi-Hamiltonian G to the M space. So basically I'm looking at the moduli space of flat connections which has a framing at this marked point on each of the boundary components, and this space has this geometric structure of being a quasi-Hamiltonian G to the M space. This is just a slightly different way to rephrase the statement which is in their paper, which is perhaps slightly more intrinsic.
That groupoid is a groupoid over the set of boundary components?
I'm looking at the homotopy classes of paths with the endpoints in this set.
What is the base point space of the groupoid?
I'm just telling you precisely, the fundamental groupoid is a well-defined thing, the homotopy classes of paths. I'd prefer to phrase it in this way.
There's chosen marked points on each one.
So it's
It just looks a bit different than what I'm used to as the fundamental groupoid. I'm just asking.
So the fundamental group, I have one base point, and I look at homotopy classes of loops. Here I have a finite collection of points, so I'm looking at the homotopy classes of paths with end points at those marked points.
I think that's the total marked points are.
That's what I asked. Okay.
Okay, we're happy then. So once we have this structure, this means in particular that we have an action of this group G to the M on this space. And we have this Lie group valued moment map, so from our space to the group G to the M. So the point is I can then just take the quotient by this group, and I have an algebraic construction, or rather they have an algebraic construction of the Poisson structure on this space. And it's isomorphic to the space of representation of the fundamental group that we're interested in to start off with. But it's a slightly better perspective because we're starting out with a space here which is a smooth affine variety. And you can look at the symplexic leaves. These are obtained by these multiplicative symplexic reductions. So I look at mu inverse of C. So C is a conjugacy class in this group G to the M. So this is just the choice of a conjugacy class for each boundary component. So basically you want to fix the conjugacy class of monogamy around each of the boundary components. So this gives a nice algebraic symplexic structure on these spaces. Okay, so these are the spaces we would like to try to generalize. So I'm hoping that these are very familiar to people here, especially the people who went to the courses last week. Okay, the other property of these spaces which I'm interested in is this. So suppose I now vary the curve. Suppose I have a smooth family of these surfaces over a base space B, like this. So each of the fibres is now a Riemann surface as we had before. Then there's a natural action of the fundamental group of the base on any of the fibres. The spaces fit together into a family of spaces over the base, and this family of spaces has a natural flat complete Ehresmann connection on it. And if I take the monogamy of this connection on this bundle of moduli spaces, there's a natural action of the fundamental group of the base on any of the fibres. So we have this algebraic Poisson action in this way. So Simpson would phrase this slightly differently. He would say that the Betti moduli spaces form a local system of varieties. That's just a different way to state that I have a complete flat Ehresmann connection on the family of moduli space over the base. It can also be looked at as the non-abelian Gauss-Manning connection, if that's helpful to people. Okay, so these are the basic properties that the spaces have. Lots of people have looked at these monogamy actions in different cases. So now I want to take a slight pause and sort of talk slightly more philosophically about what the spaces are that we're having a look at here. So it's the space of representations of the fundamental group. Is it possible to remove the bit at the top which says in-gang 1? Is there a technical... So it says here, I now want to fix a... what does it say? Sigma equals sigma bar minus these m marked points. I now start out with a punctured, smooth algebraic curve rather than having a Riemann surface. I want to take a more algebraic perspective. The point is that spaces such as this were first looked at in Riemann's work on the Gauss hypergeometric equation. These are spaces which classify algebraic differential equations. So the usual perspective that people have is probably this, at least the people in the audience here, is that this is isomorphic to the space of flat connections. So it's the isomorphism classes of pairs consisting of a smooth vector bundle and a flat connection on that. So this is perfectly true, but it's not algebraic. One would like to have an algebraic moduli problem here. So one can do slightly better by observing that the holomorphic connections are automatically flat. So it's also true that there's an analytic Riemann-Hilbert isomorphism, that this space is also isomorphic to the isomorphism classes of pairs V-nabla, such that nabla is a holomorphic connection on a holomorphic vector bundle. So this is a step in the right direction. The third perspective is this. It's also isomorphic to the space of pairs V-nabla, where V is an algebraic vector bundle now, and nabla is an algebraic connection. But now you need to put in this extra condition. You need to restrict to the connections which have regular singularities. So this statement was proved in arbitrary dimensions by Deligne, And Plummelge did something on P1 which has the same type of flavour, so I've put Deline Plummelge here. So a connection has regular singularities if and only if solutions have polynomial growth as you go towards the poles, and that can be phrased this way, that they're isomorphic to the restriction of a logarithmic connection on the compact curve. So on a curve, a connection is logarithmic if and only if it has first order poles. And so the connections which appear here are just restrictions of connections on the compact curve which have poles of order 1. Okay, so now we have this algebraic perspective over here, and this means in particular we can construct algebraic moduli spaces, and people are particularly interested in the transcendental map from the spaces on the left to the spaces on the right. The point is that both spaces now have algebraic structures, and the map that takes a connection to its monodromy is an analytic map, and in particular the cases it can be expressed in terms of polylogarithms. So this goes back to the work of Lapo-Danilevsky on P1. So this in particular was the reason that Deline was interested, that there are these two different algebraic structures there. Okay, but it's now also clear what to do to generalise this picture, that we have this very clear restriction over here, that we're looking at connections that have first order poles that have regular singular behaviour. So we can have a look at the extended version of this, where we remove the restriction over here, we just look at all algebraic connections, or upstairs we just look at arbitrary meromorphic connections which are restricted to have poles on this divisor of marked points. And so Birkhoff was the first to look at Riemann-Hilbert maps in this case. He has a paper from 1913, but only much more recently was this full correspondence worked out about 20 years ago. So basically you need to enrich the representation of the fundamental group over here by adding in the Stokes data as well. And our basic aim is to look at Poisson or symplectic moduli spaces of Stokes data in this talk. So this is a project I've looked at from various different perspectives. So the first thing that you would want to do is to extend the Atiyah-Bott complex symplectic structure to this case. It's also possible to extend Hitchens' work on hyperkähler metrics as well. This was looked at in work with Bickard from 2004. The purpose today is to talk about the algebraic Poisson and symplectic structures over here, and how to sort of extend quasi-Hamiltonian geometry such that we can construct these moduli spaces as well. So from a quasi-Hamiltonian perspective, it's basically a statement that this is a story which is about more than just Riemann surfaces with boundary, that it's possible to capture this extra data as well by adding on some new quasi-Hamiltonian pieces. So I suppose the basic point is that it's possible to describe the spaces which appear over here completely explicitly, and you just get more complicated monodromy relations. And one would like to view those relations as quasi-Hamiltonian moment maps, and that's what we do at the end of the day. So basically at the end of the talk, by the end of the talk, I hope to be able to describe what the spaces are here. So the point is that Stokes data is a very complicated thing, but I will nonetheless give the simplest description which I know. Okay, so let's backtrack slightly to give more details about the standard perspective, the quasi-Hamiltonian perspective of Alexeyev, Malkin and Mine-Renken. So you start out by defining what is a quasi-Hamiltonian space with the action of a group G. So probably most people here are very familiar with these axioms. So it's like a more complicated version of the axioms for a Hamiltonian G space. So in particular, the 2 form which appears is not closed, but is the pullback of the natural 3 form which is on the group. And there are other axioms which correspond to the moment map and non-degeneracy conditions. Okay, and then there are various operations which appear. It's possible to fuse 2 quasi-Hamiltonian spaces, and so the basic examples are the spaces which are attached to a Riemann surface with one boundary, plugging that surface into the theorem that we talked about just now, and if I glue that into 2 of the 3 holes of a 3-hole sphere, we end up with a new space which is the fusion of the spaces which corresponded to the 2 pieces over here, and there's also this reduction which corresponds to gluing on a cap, and this produces a symplexic manifold if it is smooth, simply because the axioms reduce to the axioms for a symplexic space if I take the groups to be trivial in the axioms for quasi-Hamiltonian G space. And as I guess most of the people here know, the basic examples are the conjugacy classes, which are the multiplicative versions of the coadroids orbits, the double, which is just the space attached to the annulus, so this has 2 boundary components and so is naturally a quasi-Hamiltonian G cross G space, and then the internally fused double, which is the space which appears from a one-hole elliptic curve, if you like. Okay, and they proved that it's possible to construct all of the moduli spaces attached to surfaces with a boundary from these pieces. You basically take a copy of the internally fused double for each handle and fuse them together with some copies of the double and then reduce to end up with this smooth affine quasi-Hamiltonian G to the M space. And if we look at the reductions of this choices of conjugacy classes, we get the well-known description of the symplexic moduli spaces. So the basic aim is to find the new pieces which appear when we look at the Stokes data. So I haven't told you what the Stokes data is, but let me tell you straight away sort of what the pieces are that we construct, and it will turn out that these pieces are enough to construct all of the spaces that we're interested in. So the basic statement is this: you choose a pair of opposite Borels, let T be the maximal torus, their intersection, and let U plus and U minus be their unipotent radicals. So for instance, for GLNC, I could take U plus to be the upper triangular subgroup, U minus to be its transpose, and T to be the diagonal matrices. So the basic statement is that if I just take the product of G cross T cross R copies of U plus cross U minus, then this is a quasi-Hamiltonian G cross T space for any R. So the moment map looks like this. And so one surprise, so straight away if you have a look at the first case which appears, so at the end of the day this will correspond to connections which have a pole of order 2. If I just take the straight quotient by G, so this will be a quasi-Hamiltonian a quasi-Poisson T space, but because T is abelian, it's actually a Poisson T space. This is actually isomorphic to the dual Poisson Lie group G star as a Poisson manifold. So this is the space that you want to quantize to get the quantum group. So the more geometrically minded people here may not be familiar with this, and so I've drawn this picture. So basically the quantum group is this non-commutative, non-co-commutative Hopf algebra, and there's various ways to simplify it like this. The standard perspective is to pass over here to the universal enveloping algebra, which is non-commutative, but it is co-commutative. At the bottom, you can look at the functions on the algebra, which is this Poisson algebra, which is both commutative and co-commutative. But over here, you can look at the functions on this non-commutative group G star. So this is commutative and non-co-commutative. And there's a theorem of De Concini Katz-Procesi, that it's possible to choose an integral form of the quantum group and then put q equals to 1 such that you do get precisely the Poisson algebra of the functions here. So I think Drinfeld had earlier proved a formal group version of this, but I think this statement is really due to these people here. So from the perspective of quantum groups, it's like the most important Poisson space which appears, and I'm stating it appears as a moduli space of connections which has a pole of order 2, and so that basically says that the theory of quantum groups is about quantizing a simple space of Stokes data. But we know that there are lots of connections which have higher order poles on different curves, and so one would like to construct those simplexically or Poissonly, and then ask about quantizations afterwards. It's clear even in the first example that there's an interesting quantum picture above it. Okay. So the next class of examples which appeared were these spaces of van den Berg, as far as I know. So he took a pair of complex vector spaces V and W and looked at this space of pairs. So A is a map from W to V and B is a map from V to W, and he imposed the condition that the determinant of 1 plus AB is non-zero, and that's equivalent to 1 plus BA being invertible as well. And he showed that this is a quasi-Hamiltonian GLV cross GLW space where these act as automorphisms of the vector spaces in the natural way. And the moment map is this. And he used these spaces to construct holomorphic symplectic structures on these so-called multiplicative quiver varieties of Crawley, Boovian, Shaw. What he did not point out, however, is that these spaces are very well known, and they appear in the classification of regular holonomic D modules on a disk. But from this perspective, so the quasi-Hamiltonian structure was not known before, though. So even these examples here are basically to do with connections on curves as well. Okay. So at some point around 2009, I then went back to the examples I'd looked at before and extended it slightly. So now I am able to take a pair of opposite parabolics, and so now in the case of GLN, I'm basically looking at sort of block upper triangular subgroups rather than the Borels which I looked at before. Take H to be their intersection, and take U plus and U minus to be the triangular unipotent groups which correspond to these. They're unipotent radicals. And it's possible to prove this extended statements where I now put H over here and these U plus and U minus in the middle. This is a quasi-Hamiltonian G cross H space, and now we have this group H being non-commutative. This is actually a big step, because at the end of the day we want to glue these spaces end to end with R's and H's which change in like a nested sequence. So the possibility of having this non-commutative H meant that we're able to construct a lot more spaces, and these turn out to be the spaces which do appear in the irregular Riemann-Hilbert correspondence. So the moment map looks as before, and basically these triangular matrices which appear in the middle are the Stokes data of the simplest type of meromorphic connections, the ones that just have one level. So now we can see how these van den Berg spaces appear from this perspective. Suppose I take G to be GLV plus W and H to be this block diagonal subgroup, and the U's to be these triangular groups like this. Then I can just do the quasi-Hamiltonian reduction at the identity by the group G and write down explicitly what the space is. I have this moduli relation. The G action is free, and so that just kills the G part. And so we see that this space is a quasi-Hamiltonian H space. But if you work out explicitly what it is, it's precisely the space that van den Berg had a look at. And so we have this generalization of the van den Berg spaces, first of all having more vector spaces and also having arbitrary reductive groups as well. Okay. Vandenberg was interested in these because he was having a look at these non-commutative quasi-Hamiltonian structures. I would expect that the GLN version of these fission spaces also has a non-commutative picture, but I don't see how to get the cases for arbitrary reductive groups from that perspective. Perhaps it is possible, but I don't see how to do that. And somehow from the Langland's perspective, you do need to work with arbitrary reductive groups there. Yeah. Okay. So it's also possible to draw pictures of how these spaces behave. I should point out these are just pictures. What is actually happening is squeezed into the pole, but as if you can pull it out and draw pictures, but they are just pictures. I don't actually have this structure on the surface. It is just squashed into the poles. So it's well known how to picture the double, and this is the space which appears if I take my parabolics to be the full group. So the fission spaces can be pictured in the same type of way. So basically, you reduce the group from G to H, that you're breaking G to this subgroup H, and the Stokes data gives you a precise way to cross this red line. Martinet and Rami speak about the analytic halo which you're supposed to cross in order to understand the Stokes data, and so the line which appears here is supposed to remind you of the analytic halo which they spoke about, but I have pulled it out of the pole and drawn an actual picture of it though. So typically what happens is that the group H is a product of other groups, and so we're able to reduce from G to H, and then H may break up as a product, for instance, as H1 cross H2, and so this means it's possible to glue on a quasi-Hamiltonian H1 space and a quasi-Hamiltonian H2 space. So a more accurate picture is that after you've crossed over, the pieces of the surface in the middle are completely independent and can drift apart. So a better picture is perhaps this. And I call this the fission operation. It isn't the inverse of fusion, but the word fission appeared to be available, and that's why I put it here. Okay, so at the end of the day, from the moduli theoretic perspective, the fusion construction gives you a possibility to do induction with respect to the genus and the number of marked points. Fission will enable us to do induction with respect to the order of the poles of the connections, more precisely with respect to the number of the levels which these connections have, but that's basically the order of the pole. So now I wanted to very quickly sketch an example. I don't want to do this in complete detail. I'm hoping some aspects of this are familiar to people. So I want to fix a coadjoint orbit, so O in G star, where G is GLM, and this has Maxwell torus T, which is C star to the M. So you can look at these spaces, the symplectic quotient with respect to T of these GLM coadjoint orbits at some value of the moment map. So in Alan Knutson's thesis, he looks at the compact version of these, and he called them weight varieties, and so I will call these the complex weight varieties. So these are the things, I suppose, that you're supposed to quantize to get the weight spaces, rather than quantizing O to get the full representation of G. So in particular, there's a well-known duality picture here, that this space is isomorphic to a symplectic quotient like this for a different group. So here I've got GLN, and I've got these M coadjoint orbits of GLM, and I'm looking at the symplectic quotient of the product of these at a particular orbit O check by this group GLN. So this has been looked at. It's basically the complexification of a slight generalization of Gelfand-McPherson duality. From the point of view of polynomial matrix integrable systems, it was looked at by Adams, Harnad, and Hurtubise. From the perspective of meromorphic connections, it was looked at by Harnad, who related it to work of Jimbo and Miwa on isomonogamy. Now, I guess it's actually work of Jimbo, Miwa, Mori, and Sato. Nonetheless, I think Harnad's perspective is the best, because looking at that carefully, you understand that what's actually happening is the Fourier Laplace transformation for meromorphic connections. So a point over here is basically a isomorphism class of Fuchsian systems, so a connection on the trivial bundle over P1 having first order poles where you fix the residues to be in the fixed orbits. And the Laplace transformation of these, when defined properly, is a connection which has a pole of order 2 and a pole of order 1. So we see what the weight variety actually is. It's a moduli space of connections of this form, having a pole of order 2 and a pole of order 1. So the positions of the poles here match up with the eigenvalues of this coefficient of the pole of order 2. So A0 is the diagonal matrix whose entries are these AIs. This is an important fact, because in order to get the braiding which appears, you want to move these pole positions. This corresponds to moving this irregular part over here. And we can see how to generalize the irregular part in lots of different ways, which I'll get to in a minute. But in this basic example, the spaces over here are isomorphic to the spaces over here. We also know well how to look at the multiplicative version of this. We can take the monogamy data of these Fuchsian systems. So we end up with this multiplicative simplex quotient. So basically the CIs here are the conjugacy classes which appear by exponentiating the coadjoint orbits we have here. So the space of representation of the fundamental group of this m+1 punctured sphere will look like this. So what we would like to do is work out what to put here. So the first guess would be this, that you want to look at the multiplicative version of the weight space to be this. You would like to do the multiplicative symplexic quotient by T of this space C. But C is a quasi-Hamiltonian G space. It is not automatically a quasi-Hamiltonian T space. You can't look at the dual of the inclusion to get a map from G to T. So we do the next best thing. What we do, we fuse with the fission space. So this space is a G cross T space. I do the diagonal G reduction here, and so this ends up as a quasi-Hamiltonian T space. So the fission gives me a way to break from G to T. I then do the reduction with respect to T. This is a perfectly well-defined thing now. And it turns out that this space is isomorphic to the space which appears over here. So the simplest examples of these irregular moduli spaces are actually isomorphic to the well-known regular singular spaces which appear. But once we're over in this perspective, we know that there are lots more spaces, and these have complete hypercalometrics and things like that as well. In this example, the space in the middle is basically isomorphic to a symplexic leaf of this dual Poisson B group. And there is a transcendental map from here to here, which is the map which takes the Stokes data of this connection there. So I wanted to briefly mention this paper of Doistermat. So he wrote a short paper about the similarity between the Iwasawa projection and the diagonal part map. So this turns out to be related to this picture over here, because the moment map here is the diagonal part. You're taking the diagonal part of O. Whereas over here you have this multiplicative version of it. So what Doistermat proved was that it's possible to twist the exponential map such that the diagonal part map becomes the Iwasawa projection, which is picking out basically the A part of the KAN decomposition of an element of G. this was related to my work because I observed that down the bottom here, if you look at the version with compact groups, that this Stokes map does indeed convert the diagonal part into the Iwasawa projection. And the twisting which appears is basically the connection matrix between the first order pole and the pole of order 2 here. So there's this natural class of Doyster maps which appears by having a look at the Stokes data for these connections having poles of order 2. This paper went on to become the well-known Ginsburg-Weinstein isomorphisms between K star and K star, and these also appear in this way, or examples of such maps also appear in this story as well. It's if there are examples which appear in nature by having a look at the Stokes data of connections having poles of order 2. Okay, so now I want to describe the general picture. What actually are the spaces which generalize the representation of the fundamental group that we looked at before? So previously we had a surface and we attached this Poisson space. It turns out to be very helpful to phrase the generalization of this story to start out with a generalized curve, an irregular curve I will call it, and I'll attach to that a Poisson space which you could call a wild version of character varieties, or an irregular Betti space. Nonetheless, this will be a Poisson space. So what is an irregular curve? So basically you need to fix an irregular type at each marked point, and an irregular type is this. So I've fixed my complex reductive group in a Maxwell torus T, and T in G are the Lie algebras. So if I have a marked point on a disk, then an irregular type intrinsically is an element of tk hat modulo to hat. If I choose a coordinate z which is equal to 0 at the marked point A, then k hat is just this, the formal Laurent series, and O hat is the completion of the germs of holomorphic functions. And so then an irregular type is just the principal part of a t-valued meromorphic map. So I can write it out explicitly in this way, so the coefficients are elements of t. It's good to have the intrinsic perspective, because at the end of the day we want to vary the irregular curve, just like we varied the surface before, and for this it's good to have a coordinate independent perspective. But at the end of the day it's just a choice like this. So an irregular curve is just a smooth, compact, complex algebraic curve having m distinct marked points and the choice of an irregular type at each marked point. So as I said before, the aim is to construct a Betti moduli space for each such curve, and these. So I'll describe what these spaces of monogamy data are. These will be isomorphic to certain moduli space of connections with higher order poles. They will classify connections which can locally be written in the form like this. So it's dq plus terms which have first order poles and less singular pieces. So the q here gives you the irregular part, the parts with poles of order 2 or more. And this means if you look at local solutions, they involve terms of the form e to the q. So in particular, they have this non-polynomial growth, let's say. They have these highly singular parts. And so the irregular type, which turns out to behave just like the moduli of the curve, controls this exponential growth part. Okay. So now I need to describe what the Betti spaces actually are. So the point is that Birkhoff first looks at the irregular Riemann-Hilbert correspondence in 1913, and this was worked out completely in the 80s and 90s in work of Boalch, Lutz, Malgrange, Sibuya, Deline, Martinet and Ramis, and there's various different perspectives on how to describe this Stokes data. So Deline has a nice sheaf theoretic perspective. Malgrange and Cebu have a non-abelian cohomological perspective. The perspective I'll give here is closest to that of Martinet and Ramis, which is basically the most explicit possible, I think, and involves ideas related to Eckal's work on multi-summation. But I'll look at the extension of this to arbitrary reductive groups as well, and describe it in terms of groupoids in a quite concrete way. Okay, so what do? We start out with this irregular curve, and we have these marked points in irregular types. I want to look at the real oriented blow-up of this curve at each marked point. So I replace each of the marked points by the real oriented directions emanating from that point. So basically I'm replacing each AI with a circle. So I now have this surface with boundary, with these M boundary components. And now there's some combinatorial data which is determined by this irregular type. This is explained very carefully in the paper, so I'm tempted to skip over it quite quickly here. So the data is basically this. You get a connected complex reductive group at each marked point. This is the centralizer of Q, so it's just the subgroup of G which commutes with all of the coefficients of Q. Then you get a finite set of singular directions, so this subset of this boundary circle. These are distinguished directions where the growth rate changes if you look at e to the q or e to the add q. And then on each of these singular directions there's a well-determined unipotent subgroup of G, the Stokes group. And this is a unipotent subgroup which is normalized by this group HI, this reductive group HI. So that's the basic picture. I hesitate to give you this in detail because it's technical, but nonetheless, let's have a go. How much time do I have? Okay, so the HI is the centralizer of Q, as I mentioned before. So to define the singular directions, well, let's let R be the roots of G with respect to T. So G breaks up in this root space decomposition. So G alpha is the root space corresponding to the root alpha in T star. So for each root alpha, I can compose with Q if I'm fixing it at a particular irregular type Q. So Q alpha here is a germ of a meromorphic function, whereas Q was a T valued. I now have an actual function for each root. And I can look at the behavior of this. And so I say a direction is singular, supported by the root alpha, if the exponential of Q alpha has maximal decay along that direction. So if I look at how e to the q alpha grows as I look at all of the different directions, the directions on which it has the maximal decay are the singular directions. This is a well-defined finite subset of this boundary circle. And then I can define the Stokes groups like this. So for each singular direction, there's a well-determined subset of the roots such that that root supports that direction D that it appears in this statement over here. So for each direction I have a well-defined collection of the roots, and I can look at the exponentials of all of the root spaces and the product of those in G, and this is a well-defined unipotent subgroup, independent of the choice of order of the product here. So the picture is this. I have a surface. I'm drawing the picture that just had one marked point. I've taken the real oriented blow up here. The red dots are the singular directions. What I now want to do is add an extra puncture in the interior near each of the singular directions, and I draw some dots so that if I do a diffeomorphism, I don't forget that this singular direction matches up with this puncture over here. So we end up with this punctured surface, and we can look at the fundamental groupoid of this. So just as before, we choose a base point on each of the boundary circles, and we let pi be the fundamental groupoid of this with this fixed set of base points, one on each of the boundary components. So I can look at loops that do things like this and that can go inside as well, these extra punches. So I've got a fundamental groupoid of things like this. So if we just looked at this fundamental groupoid, we'd basically be in the situation we're in before. It is equal to the fundamental groupoid of a surface with boundary as we had before. I want to look at a subset, the subset of Stokes representations, which obey two extra conditions. So first of all, if I have a loop which goes around inside, then I want to look at the representations that take such loops into this distinguished group HI. And if I just go around a bit and around a puncture, then it has to take these into this distinguished Stokes group, STO-D. So I do this for each marked point and each puncture at each of the marked points. And if I was to go this way, it's well defined because the HI normalizes the Stokes group. Okay, so I have this well-defined subset, and the main statement which generalizes the statements of Alexeyev, Malkin and Meinl-Brenken is this: that the space of Stokes representation is a smooth affine variety which has the natural structure of quasi-Hamiltonian H space, where H is the product of these groups HI. So in effect, the irregular type Q restricts me from the group G down to this smaller group HI, and I do that at each of the poles. So if I go back to the case where I had no irregular types, then this group H would be my group G to the M, and I would have none of these extra punches, and I would be precisely in the picture that we had at the start. So I have this smooth quasi-Hamiltonian space. I can look at the reductions of that. So if I just quotient by the group, this algebraically inherits a Poisson structure, and the symplectic leaves are got by fixing conjugacy classes in the group H. This is an important fact, that we're fixing the conjugacy class which goes around the interior here. It's not the conjugacy class of the monodromy, which would be outside. This is important if you want to look at the irregular analogue of the Deligne-Simpson problem. I think the correct thing to do is to go around the inside. This gives the moduli spaces which have the which we know have the hyperkähler metrics. Okay. So a consequence of this, so supposing you weren't interested in the symplectic or Poisson structures, just interested in the underlying differentiable manifolds, this perspective nonetheless gives you a way to prove that for generic semi-simple classes, the irregular Betti spaces are well behaved. So there's this symplectic fact that if I have a locally free action, then the subvariety cut out by the monodromy relation is smooth. So this fact has a quasi-Hamiltonian version, and we can use that to construct the Betti spaces here. So you can prove that these are algebraic symplectic orbifolds for arbitrary groups. But if you look at GLN, you can do better and prove that they're actually smooth symplectic algebraic varieties. So this extends a result which I guess goes back to Gunning, where he looked at the usual case where he differentiated the monodromy relation. One could try to extend that type of approach here, but the space of data which appears is very much more complicated, and you sort of really don't want to differentiate the monodromy relation explicitly. So the quasi-Hamiltonian perspective enables us to avoid that and gives a way to prove quite nicely that you do end up with symplectic, smooth symplectic spaces for generic orbits. Okay, so we do have this picture that an irregular curve determines a Poisson space. So the other fact we wanted to understand is What happens if I vary the curve? So as I briefly mentioned before, the irregular type behaves like the moduli of the curve, and so that's part of the reason we have packaged up the irregular type into this definition of an irregular curve. So we would like to know which deformations of these can we do such that we do have this local system of moduli spaces like we did before. So the basic definition is this: if I have a family of irregular curves, so for each point of the base B I have an irregular curve, this deformation is admissible. So as always, you would like the fibres to stay smooth and none of the marked points to coalesce. And the extra condition is this, that for each root, the pole order of this meromorphic function alpha composed with qi has to stay constant, that you don't want the order of the pole of this to change. And this turns out to be the right thing to do. The statement is that if you have an immiscible deformation in this way, then we do indeed have an algebraic Poisson action of the fundamental group of the base of the family on each of the fibres. So this extends Simpson's statement that the Betti moduli spaces form a local system of varieties, and adds the word Poisson or symplexic if you look at the symplexic leaves as well. So this is a natural class of actions which generalizes the well-known braid and mapping class group actions. If we go back to this first example, which was this Laplace transformation, I had the braiding of the position of the poles over here and the braiding of the irregular types, the coefficients of the pole of order 2 on the other side. But now I'm able to look at it for arbitrary groups. Well, let me just describe the basic examples. First of all, if I just take G to be C star, the abelian case, we don't get sort of new interesting moduli spaces here, but nonetheless, being in this country, it's good to make a link to KDV. So if I look at C star, then the fact is that the Baker functions are horizontal sections of such irregular connections on spectral curves. And Krzysztof shows how to use the Baker functions to give explicit algebrogeometric solutions to KdV. And one can easily observe that the times which appear here are just these irregular deformation parameters which I'm speaking about in this case of C star. So normally Siegel, Wilson and people will write them down in this way. In fact, I think everyone does. They use a coordinate W which has a pole at the marked points rather than a 0. But this is, the coefficients of this are just the irregular type that we were speaking about. And so the times appearing in KdV match up with these irregular deformation parameters in this case of C star. So we're extending this. This was first looked at in the case of GLM by Jimbo and Miwa. And I'm extending it to other reductive groups of these extra sort of depth as well. So the simplest example is having a pole of order 2. So the admissible deformations of this, if I take A0 to be in T reg, is just all of T reg. We just stay off of all of the root hyperplanes, that all of the deformations here are admissible provided A0 stays off of the root hyperplanes, and the fundamental group of the base here which appears is the pure G braid group. So this is the basic braid group action which underlies this quantum vial group action if you quantize it. So the fact is that we now naturally get the G braid group actions, whereas in the past it was just the mapping class group and the type A braid groups which appear from sort of the motion of marked points on curves, that we now get the structure group appearing as well. Okay, so I wanted to explain, sort of roughly speaking, how the proof works. Maybe I'll just sort of state how it works. So we've constructed these basic pieces, the fission spaces. We can just look at all of the the quasi-Hamiltonian or symplectic spaces which appear by fusion and reduction of these spaces and conjugacy classes. And the basic statement is that the spaces we wanted to get to are within this class of spaces which are generated out of these basic pieces. I can fuse these together in order to get these complicated Stokes groups which I described briefly. So this could be phrased as being that the irregular Betti space is a fission variety. So the picture for how this works is basically this. I have an irregular type. It has these coefficients. You want to start at this end and work down. So you start out with the group G, and then if I look at the centralizer of this coefficient AR, I end up with a smaller group HR minus 1. Now if I look at the centralizer of the first two terms, I get this nested sequence of reductive groups defined in this way. So the space of Stokes data which appears attached to Q, I can define it to be AQ to be the product of the Stokes data with the group G and the group H, which appears at the bottom here. So we would like to prove that this space is a quasi-Hamiltonian G cross H space, and we can prove that because it's got by gluing these fission spaces together in this nested sequence. So here I do the diagonal reduction with respect to the HR minus 1 factor here, and the coefficient at the top goes down. Also have this nested sequence of groups with decreasing coefficients. So the statement is that this gluing here is isomorphic to the space which we wanted to get, and the picture should be something like this, that you're breaking the group in this nested way. So at the end of the day, we're able to describe precisely what the monodromy relation is. This was the starting point that we, you look in books on Stokes data and you see it's possible to describe the Stokes data in this way, and you think, well, there's this nice quasi-Hamiltonian perspective, and this appears to be the best way to understand monodromy of flat connections. Is it possible to extend that to include these extra pieces which appear here? So basically the story is as before, except we've replaced the doubles which appeared here by these quasi-Hamiltonian G cross H spaces AQI, and this is encoded in this extra data that we put on the boundaries, and the monodromy relation looks like this, where the pieces here are now more complicated, which is the G moment maps for these spaces A of Q. So at the end of the day it looks like this. It's the product of the Stokes data which corresponds to the monodromy around the puncture. Okay, so we've kind of got to where we wanted to go. You can also observe that there's lots of other spaces which appear. We don't know in general if all of the spaces which appear have the good properties that the wild character spaces. I mean, we know that this is an explicit algebraic description of the complete hyperkähler manifolds which were constructed in this work with Bicard, extending that of Hitchin. If you look at arbitrary fission spaces, one would like to believe that these also have nice hyperkähler metrics, but I don't know how to prove that. In particular, it's possible to obtain all of these Crawley-Bouvier-Shaw multiplicative quiver spaces by passing through this work of Van den Berg. So in the paper I wrote in 2009, I drew this simple example. It's possible to look at spaces where the groups change on different parts of the surface just by performing this fission operations. So it's easy to cook up lots of examples of the symplexic moduli spaces which appear, which are beyond the class of wild character varieties. Okay, so the last thing I wanted to say, so the story we were really interested in was constructing these symplexic structural moduli spaces. We then looked at the families of moduli spaces as the irregular curve moved, and this family had a natural flat complete error swing connection. And we looked at this in terms of moduli data over here. If you pull that back to the connection picture, if we pull it back along the Riemann-Hilbert map, we have a complete flat connection on a family of moduli spaces of meromorphic connections on a family of algebraic curves with varying curves, marked points and irregular types. If you look at simple examples of this, when these fibers, these symplectic spaces are complex dimension 2, this connection can be written down explicitly and gives you the non-linear Pain-Levé equations. There's basically 6 examples which appear where the moduli space has dimension 2, and I've been sort of thinking about these in various directions, and that was sort of most of the motivation to understand the moduli spaces which appear there and their higher dimensional versions. I was very happy to see that there was a talk advertised of Doistermatt where he has begun to see part of the beauty of the Pain-Levé equations as well, that he was enthusing here about the amazingly rich structure of the solutions of the first Pain-Levé equation, the very simple differential equation y double prime is 6y squared plus x. So I will stop there. Thank you.